so we have another speaker ready. We'll be speaking now from Ismael Lucas de Paiva. You are now based in Israel with
Bristol.
Bristol, okay, sorry. Yeah, very good. Yeah, right there. He's based in Bristol and he will tell us about complementarity trade-offs and relativistic mathematics. So the stage is yours, and watch out your response.
Thank you. I want to start to thanking the organizers. It's been like a fun and very interesting event. Like as usual, it's so awesome that we have like every year this type of event where we have a bunch of people just interested in talking about topics. So very nice. So yeah, I'll be talking about complementary relations and relativistic scenarios. The type could also be Wigner rotation effects with complementary descriptions, because I will consider basically particles existing this scenario. So I worked developed with Marcus Bristol, who is a PhD student in the Federal University of ABC. Although the name, it's not a university created to teach the alphabet. ABC is actually the name of an area in São Paulo. And Pedro Diegues, who is a postdoc at the International Center for Theory of Quantum Technologies in Paulo. So, yeah, first I will introduce the type of complementary relations I will be analyzing, and then the type of interferometers I will be using as a reference in this study. Then with this I will introduce Wigner rotation, and then I can analyze the complementary relations in space-time. And to make the discussion more concrete, I will consider the Newtonian law. So, first complementary relations. Typically we consider an inequality like this first one. So we have visibility and path distinguishability. But sometimes it's desirable to complete it to get an equality instead of this inequality. Because, for instance, if you put a maximally mixed state inside the interferometer, both visibility and path distinguishability can vanish. So there is some element that's missing. These elements typically associated with entanglement, some metal entanglement. So sometimes it's desirable to compute. But the complementary relation I will consider still won't involve directly visibility, because I will consider this one here. The first term is the path relative entropy of coherence, which is like the relative between the state of the system and the system dephased in this z basis. The z basis is associated with the paths. 0 and 1 I will consider two path interferometers. The other quantity is path predictability, which tells me how much the probability distribution between the two paths differs from an even distribution, half and half. And the entropy of the system, which I can understand as the entropy of entanglement with a purification of the system. So a lot of times just with reciprocal coherence, predictability and entanglement. These last two give me some notion of path distinguishability, while in the first one, there is a sense in which I can understand a bit like a wave-like behavior, make a difference between a wave-like behavior and a path-like behavior. Because if I have path coherence, it's like having a wave-like behavior, so that I have a maximum of classicality in a sense of the particle inside the interferometer. But if I have zero path coherence, I could be just as well sending particles like on each path, like distinction. So this is the type of relation we will be studying, and then the type of interferometer we will be using as a basis. We actually be using two interferometers. The first one is this one, which is a variation on Wheeler's late choice experiment. Because in Wheeler's late choice experiment, we can decide or not to add the second beam splitter to the Maxander, and so it's a classical control. But there is like this quantum late choice experiment, because you make the choice quantum, you basically put it in a superposition, the second beam splitter, in a superposition of being inside or outside the interferometer. And so yeah, you start with a system here and time to 0. After the system crosses the phase shift, you have the state, and then after it leaves the interferometer, it is the state of the system. And I could, again, no space time here, I could compute the relations, the complete complementarity relation for this state in the middle, and also I could use the final state to compute visibility. So the point is that because visibility depends on the square of the cosine of alpha, and alpha is associated with how much this is present here, it's understood that's like, oh, we have a hybrid behavior of wave and particle inside the interferometer because of this type of visibility. However, if you consider the state inside, of course what we get is coherence, path coherence maximum. So if you think as like a potential of interfering, you still have a maximum potential of interference. You have potential to get maximum visibility. So some people are not completely satisfied with visibility as a notion of, like as a measure for particle wave-like behaviors. So, and that's why sometimes they prefer to use these other notions and even analyze the state that's assigned in the middle. But it turns out that for this, even for if you think like that, there is a simple solution here, which simply involves swapping these two beam splitters. Because now, if you compute the states like in the same locations, you take the state in the middle and the quantities in the complementarity relation. Here we already have coherence, so we see when it's 0, so we have coherence 1, so it's like a wave-like behavior. When it's alpha is pi over 2, it's like this is outside, so we have a particle-like behavior, and we have something between. So as a maximum potential of interference in a sense of visibility for the other values of alpha. And visibility is the same. So if you prefer to use visibility as a measure, you can still do the same analysis if you prefer. So we'll be using both. We'll be using the two in our analysis because it's actually very easy to get one expression, expressions for it. Now, begin rotation. This is like a relativistic effect. Then, just to talk about it, I first need to introduce a local Lorentz transform, and this is the main reference for this entire part on linear rotations. This book in quantum information and gravitational fields. It's really like for the heavy part of, like more technical part of this work. It's basically done in this book. In a sense. It's a nice book. So to get a local Lorentz transform, we could start choosing a tetrad field, and then what we want to see is, for instance, is like how momentum our system will change after it moves from a certain location to a location that's infinitesimally close to it, and this change in momentum will depend on this sum here, and we can see that the first term actually depends on non-gravitational forces applied to the system, which is given by this expression, and the second one actually depends on the curvature of space-time. So basically, in each point you have this local reference frame, these local frames associated with the tetrads, but then you need to kind of glue them together. That's the starting moving. And this omega is the spin connection. This is what we define the spin connection. Then, if you want to write the difference in momentum in terms of this tensor of lambda, you conclude that that's how you write, and this would be an infinitesimal Lorentz transform. Now, you want, like in quantum information, we want to study the transformation of a quantum state. So basically, we want to find a representation of this Lorentz transform as a unitary acting on a Hilbert space. So we take, say, a system with a spin here, we take consider a spin hat, and then I have an eigenstate of momentum. So what I want to know is, like, if I have a unitary representation of this, how it would act on this state, for instance. Naively, maybe we would expect something like this. That we have Lorentz transform, then we just transform the momentum, and we leave the spin intact. However, this is wrong. What we actually get is, like besides doing a change in momentum, we get an extra rotation applied to the spin of the system. So basically, of course, this is an state of momentum, so we can't imagine a localized system. But we could say, oh, the particle is moving, but while it's moving, the spin is spinning, it's being rotated. And this B is the Wigner rotation, and we can, for the spin half, we can write like this. And this is the infinitesimal one. If you consider a longer path, you just integrate in a sense, and the T there is the time order in the period. Because in general, the Wigner rotations at different locations want to move. So yeah, so before moving on, like still in this part, we will use an approximation for wave packets, because of course in general we have a superposition of momentum, so it will be like a mess. But then we can use the semi-classical approximation to represent the system, like the spatial part of the system, basically by its center of mass, and then also by its average moment. Somehow the black is super tiny there. This is unintentional, but it's a P bar here, and then we just do a Wigner rotation that depends on this average moment. And because also I'm assuming that it will be constant, P bar will be constant throughout the dynamics. Okay, so now with this set, we are good to go to analyze now the interferometer. So first, in this scenario, so I will start the system. So the particle will start here from like path 0. The spin will start in the state tau, and I have this position in the splitters. Then in the middle, I represent the spin by this tau 0 and tau 1, which is like the Wigner rotation of tau, of the original state of the spin. But one is the rotation through path 0, and the other through path 1. And then I have the final state. So if I analyze the quantities in the complete complementarity relation, they will depend only on this, the absolute value of this scalar product. That is tau 0 and tau 1. And we can see, for instance, with like if you didn't have any space-time structure, you had like just like Newtonian space and time. This in a product would be 1, so it will be here. So the state will be maximally coherent, for instance, if you consider the coherence curve here, which is what we had before. But we see that this coherence tends to decrease the more relevant this term becomes. So if you have a strong curvature, you tend to go to like 0 coherence in principle. So you could have like a particle-like behavior, if you will, because it's just like a statistical mixture of one particle for the other. But of course, if the curvature is too strong, like this could go from 1 to 0 and back multiple times inside the interferometer. So you could actually, you would have some freedom to fine-tune the dimensions of the interferometer to see the effects of Wigner rotations or not, depending on what you okay. If I do in the opposite, like if I swap the Wigner splitters, I have a similar computation. And then now it's a bit more complicated because it depends on alpha and on tau, on this scalar product. But it's, in a sense, it's similar. The case alpha equals 0. It's basically when the Wigner splitter is here, so we have a Max lambda, so it's just like before, in a sense. But when alpha is pi over 2, this is outside, so just have the particle traveling here and being split at the end. So we can see that's why path coherence for alpha equals pi over 2 is 0, because you are actually in a single path. Entanglement, in a sense, to be similar, like if you split in the middle, you start getting entanglement with the spin. But if you don't, to be in a pure state, that's why it goes to 0 there. But predictability is interesting because it doesn't depend on the space-time structure at all. It just depends on the result from the control. Cool. So this is, of course, very generic. If you see these calculations, I wouldn't even need to really have introduced the linear rotation in a sense. We have just mentioned that it exists. But to make it more concrete, I can consider, for instance, the Newtonian limit. In a sense, this is not the best example because, as we see, it's basically negligible, the effects. But it's cool because in this limit, I can compare the results with a result by Magdalena and Zick. So we can have, like, we can establish this connection. And also address a question from yesterday. So in the Newtonian limit, we have this metric here. I consider z to be the horizontal direction, x to be the vertical one, and y to be the one perpendicular to the interferometer. So the interferometer. And okay, this is the expression for the linear rotation. But so we needed to find this vector theta, and it turns out that the only non-vanished component is this one, it's the y component. And it's also only non-zero when pz is non-zero. So while it's traveling in the horizontal. So so with this, I can compute because, as we saw, everything depends on this scalar product. So what I consider here for this plot is the following. I consider squared interferometers with length L. Each side has a length L. And then I was analyzing the value of this quantity while the particle is inside the interferometer. So we see, like, first a jump, like an increase here, and this is the part when the particle on path 0 is traveling the horizontal, because the one on path 1 is traveling the vertical. So there's no linear rotation in this case. Now, as soon as this ends, the particle on path 0 starts traveling the vertical, but then the particle in path 1 starts rotating. But because one is subtracted from the other, because we have a net rotation here, in this scalar product, it actually starts subtracting. So it's a bit fun because, in principle, the effect of linear rotations could be greater, but then it's almost conspiratorial. Like, in the end, it decreases because the amount of rotation on the top horizontal will be almost similar to the one in the lower path. And here we basically get subtraction of the two rotations, right? So as you can see, and this again, it's a logarithmic scale, so it's very tiny. It's like 10 to negative 44 here. It's extremely tiny. But then, okay, so since I'm here, I can talk about changing visibility. And the visibility will be given by this expression. And like in the Newtonian limit, that's how I can write this, assuming doing some approximations. I can write this as like this cosine, and again L is the length, the horizontal length. And then we can see that this expression is similar to the one that Magdalena obtained and was already mentioned here a few times in this conference. But then the difference is that in her work she had the internal degree of freedom of the particle working as a clock. So it had Hamiltonian, and then the result that was affecting visibility was the different time dilations. But it's very similar, like delta E. The only difference is the delta E over H bar, which is the difference in the level of energies of the clock. However, this effect here is many orders of magnitude lower. So in a sense, I mean, one way of reading this is that this result is correct even if you had a spin as the internal graph. So it wouldn't modify this result. And then, good. In the end, I ended up being tested that group. I actually done basically that's what I wanted to say. And yeah, so we saw how Wigner rotations can affect complementary relations, and it would be Newtonian limit, even though it's negligible, it can actually be relevant if you have scenarios with stronger gravitational fields. Now, a question that we have is like, in the Newtonian limit, if you can find clever ways to make Wigner rotations more relevant, maybe considering nested interferometers or interferometers. It would be interesting to find ways to see, because it would be a difference between just having a colored qubit and a spin as the internal graph reading. So yeah, please, I thank you for.
Thanks, that was fascinating. The interferometer with the spin, could you turn that around as a parameter estimation problem and use it to map out space-time curvature as an operational tool?
Yes, it's true.
Good.
I didn't think about it, but yeah, we could start not knowing the space-time curvature, and then you just have an interferometer, and from this you can estimate.
Okay. The curious feature then, though, is that geometry would be a little bit fuzzy and probabilistic because you're sampling distributions. That would render space-time probabilistic, which would be interesting.
Yeah, and also another issue is, like, because of the periodic structure in the spin, you get some information, but there is some modularity to the information that you can get. So there is some issues with this, but it seems it can be formulated.
Maybe I can ask my questions while other people think about their questions. So just something simple that comes to mind, because I realize now that the smallness of the effect partially it's because maybe using spin 1/2. So maybe it's one idea is how much this can be cranked up, even from the point of view of like estimating the space-time parameters. But another thing, it seems this kind of symmetry of the Mach Zehnder. So have you considered something as simple as having one of the spins always in the lower path and the other just going up and down? So like in an actual twin paradox type scenario, so you will not have the cancellation of, or maybe not to the same extent.
Well, that's interesting, because I was trying to find a clever way to avoid this cancellation. But yeah, we didn't consider this type of scenario, so maybe that's a good approach to continue this work.
I guess we can keep discussing over the break.